Connecting a machine requiring 120 volts to 240 volt high-leg delta system is not a straightforward process. The suggestion to use phases A and C, which are assumed to be 120 volts each in a Y configuration, and then somehow derive 120 volts for phase B by connecting two phases to a step-down transformer, is fundamentally flawed in a delta system. In a delta system, the voltage between any two phases is the line voltage. In the stated scenario, this line voltage is 240 volts. There is no inherent 120 volt potential readily available between phases in a delta configuration. The key principle to grasp is that a delta system provides power through the voltage difference between its phases, and that voltage is the specified line voltage, which again is 240 volts. Attempting to connect two phases, such as A and B, or A and C, to a step-down transformer, as suggested, will not result in a stable 120 volt supply. The reason is simple. The voltage presented to the transformer will be the voltage between the two connected phases, which is 240 volts. A standard step-down transformer is designed to reduce a higher voltage to a lower voltage, but it cannot conjure a lower voltage from a source that doesn't inherently possess it. The transformer requires a 240 volt input to then step down to the desired 120 volt output. The only reliable and safe way to obtain a stable 120 volt supply from a 240 volt high-leg delta system is to utilize a dedicated transformer specifically designed to convert 240 volts to 120 volts. This transformer will have a primary winding connected to the 240 volt supply, typically from two of the delta phases, and a secondary winding providing the required 120 volts. The transformer's core and winding ratio are engineered to efficiently and accurately step down the voltage from the high primary voltage to the lower secondary voltage. It is important to note that using an incorrect voltage supply can damage the machine and pose a significant safety risk. Improper wiring or voltage mismatch can lead to overheating, electrical fires, or complete failure of the equipment. Therefore, adhering to the manufacturer's specifications and employing appropriate voltage transformation methods are crucial. Always consult with a qualified electrician to ensure that the electrical installation complies with local codes and safety regulations. The high-leg delta system presents a specific challenge because one phase, the high leg, has a higher voltage to ground than the other two phases. This high leg is typically identified with orange marking. When connecting a transformer to a high-leg delta system, it is crucial to identify the high leg and ensure that it is connected to the appropriate terminal on the transformer. Incorrect connection can result in voltage imbalances and potential damage to the transformer and the connected equipment. Electrical codes, such as the National Electrical Code or NEC, provide detailed guidelines for wiring and grounding electrical systems, including high-leg delta systems. These codes are designed to ensure the safety of personnel and equipment. Always refer to the latest edition of the NEC and any applicable local codes when working with electrical systems. When selecting a transformer for this application, it's important to consider the volt-amp or VA rating of the machine. The transformer must be sized to handle the machine's VA requirements without overloading. An overloaded transformer can overheat and fail, potentially causing a fire or other hazards. The VA rating of the transformer should be at least 25% greater than the machine's VA requirements to provide a safety margin. Furthermore, the transformer should be installed in a well-ventilated area to prevent overheating. Proper ventilation allows heat to dissipate, ensuring the transformer operates within its temperature limits. The transformer should also be protected from moisture and other environmental factors that could damage it. Regular inspection and maintenance of the transformer are essential to ensure its continued safe and reliable operation. This includes checking for signs of overheating, damage to the windings, and loose connections. Any issues should be addressed promptly by a qualified electrician. In addition to voltage transformation, it's also important to consider the grounding of the electrical system. Proper grounding provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. The grounding system should be installed in accordance with the NEC and local codes. The grounding electrode system typically consists of a ground rod or plate buried in the earth, connected to the electrical panel with a grounding conductor. The grounding conductor should be sized appropriately for the system's fault current capacity. Ground fault circuit interrupters or GFCIs provide additional protection against electrical shock. GFCIs detect small imbalances in current flow and quickly interrupt the circuit, preventing a dangerous shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. When working with electrical systems, always follow safe work practices. Firstly, always energize the circuit before working on it. Use a voltage tester to verify that the circuit is energized. Secondly, wear appropriate personal protective equipment or PPE, such as insulated gloves and safety glasses. Thirdly, never work on electrical systems when wet or damp. Fourthly, be aware of your surroundings and avoid contact with conductive materials. Fifthly, if you are not qualified to work on electrical systems, hire a qualified electrician. The NEC provides specific requirements for the overcurrent protection of electrical circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the circuit when the current exceeds a safe level. The size of the overcurrent protection device should be matched to the ampacity of the conductors in the circuit. The ampacity of a conductor is the maximum current it can carry safely without overheating. The NEC provides tables that list the ampacities of different types of conductors based on their size, insulation type, and installation method. When selecting conductors for an electrical circuit, it's important to consider the voltage drop. Voltage drop is the decrease in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To minimize voltage drop, use larger conductors or shorten the length of the circuit. In summary, to safely and effectively power a 120-volt machine from a 240-volt high-leg Delta system, a dedicated 240 volts to 120 volts transformer is essential. This transformer must be properly sized, installed, and maintained to ensure reliable and safe operation. Always follow safe work practices and consult with a qualified electrician to ensure that the electrical installation complies with all applicable codes and regulations. Ignoring these guidelines can lead to equipment damage, electrical shock, and potential fire hazards. Understanding the intricacies of Delta systems, voltage transformation, and electrical safety is crucial for any electrical installation. By adhering to best practices and consulting with qualified professionals, you can ensure a safe and reliable power supply for all your electrical equipment. Remember that electrical work can be dangerous, and it's always best to err on the side of caution. If you are unsure about any aspect of an electrical installation, seek the advice of a qualified electrician. They have the knowledge and experience to ensure that the work is done safely and correctly. By prioritizing safety and following established guidelines, you can protect yourself, your property, and others from the hazards of electricity.